Good day, sir. I am Nina Rines Destora, the reporter of today. So my topic is all about In-Pond Raceway. So what is In-Pond Raceway? In-Pond Raceway, or IPR, is a fish culture technology developed to increase production, efficiency, and yield. In-Pond Raceways. The concept of the In-Pond Raceway, or IPR, was simple. It would be a system like cages that could be adapted to almost any body of water, but with the advantage of controlled water movement to improve the water quality. Vast amount of water impounded or potentially available in rivers, bays, and estuaries, and have seen opportunities to produce fish and allow for increased stocking density, thereby increasing total production per unit area. So cages, especially in private impound waters, seem to be problematic because of disease outbreaks, poor localized water quality, and slow growth. These problems often appear to be related to poor water quality circulation through the cage. Flow-through systems, such as raceways, tend to have fewer water quality issues than most other culture systems. Exchange of water removes metabolites from the culture area that allows increased stocking rates and production rates per unit area compared to cages and open ponds. Traditional raceways have to be located on springs or creeks with sufficient gradient, and these constant flowing water sources are exceedingly site limited. So next is the development of the In-Pond Raceway. In the early 1990s, an IPR was developed at Auburn University. The design used airlift pumps to move water through a box-like culture area. The raceway was rectangular and suspended from a floating pier. Airlift were placed at one end of multiple raceways, and water was pumped through the airlifts into the raceways at the surface. Water was discharged from the raceways along the bottom on the opposite end from the airlifts. The water discharged through a solids settling chamber and then flowed back into the impoundment. The construction of an IPR was relatively simple as well. The raceway box itself was constructed from 1.3 cm thick or 0.5 in thick marine plywood or 0.7 cm or 1/4 inch plastic sheeting. Cage mesh type materials, plastic coated welded wire mesh 2.54 cm times 1.27 cm were used across the airlift openings and the discharge areas to keep fish inside the raceway. The advantage of the airlift system was not only high volumes of water moved but also some degree of aeration. Although airlifts are not very efficient oxygen transfer systems in relative terms, they become more different when dissolved oxygen concentrations are low. Solid waste collection was attempted through either quiescent cone or tube-type settlers attached to the back of the raceway. These passive methods captured a portion of the solid waste excreted by the fish, which were then removed from the system. This lessened the negative impact on the water quality of the impoundment. Next is the stocking and feeding. Species that have been cultured in an IPR are the channel catfish, blue catfish, channel times blue hybrid catfish, Nile tilapia, hybrid striped bass, bluegill sunfish, yellow perch, and rainbow trout. Stocking rates in the IPR varied from 326 to 500 43 fish per cubic meter or 9 to 15 fish per cubic foot of culture area. But only channel fish and Nile tilapia were successfully polycultured in experiments at Auburn University. Feeding is a nutritionally complete diet is essential in an IPR because the fish get no natural food items from the environment. Floating feed was given to allow observation of feeding activity and to keep feed trapped behind the idly board. However, demand feeders proved to be just as efficient as hand-feeding channel fish and reduced labor requirements. Next is the backup system and disease treatments. The IPR is an energy-dependent system. If a blower fails and water flow stops, the raceways will become oxygen limited in a matter of minutes. Backup or emergency systems are essential if the system is to be successful. A simple oxygen supply was incorporated into the Auburn IPR design using cylinders of pure oxygen connected to an electric solenoid switch. When the electricity supply was interrupted, the solenoid opened to allow pure oxygen to be released from the raceway through micropore tubing. Another benefit of oxygen backup system is in IPR is during disease treatments. With the blower off and water flow stopped, emergency oxygen system can be used to maintain fish. Then the raceway became a static tank that can be dosed with bath-type treatments. Example is the potassium permanganate or formalin. These treatments are inexpensive and effective methods for combating certain bacterial and protozoal diseases. Comparison to other culture systems. This table shows the general advantages and disadvantages of the IPR compared to other systems. In the following sections, traditional raceways refers to land-based flow-through raceways, while RAS refers to recirculating aquaculture systems. In terms of production, IPR average a yield of approximately 136 kg meter per cube or 8.5 pounds or 3 feet of catfish and tilapia. The feed conversion ratio or FCR average in 1.5. Economic feasibility of IPRs showed more economically efficient than ponds and cages. The IPR designed and greater accessibility simplified feeding, grading, harvest, and disease treatments compared to other systems. This reduced labor requirements compared to ponds or RAS. The IPR also had lower production costs than are typical with RAS. The IPR with its system of passive settling devices is environmentally superior in terms of solid waste removal when compared to cages, ponds, and traditional raceways. Recirculating systems with active solids removal and biological filters are much more efficient at removal of waste product. As in ponds, cages, and traditional raceways, IPRs rely on natural processes within the receiving impoundment to process liquid wastes and solid wastes that are not removed by the positive settlers. Next is the sustainability issues. The IPR system appears to be more environmentally sustainable than cages, raceways, and intensive open pond production ponds. The IPR system is slowly being adapted to larger scale operations and appears to be highly efficient at producing fish. If this adaptation continues, the IPR could replace traditional ponds for culture of many finfish species. And then the future trends. Cost-effective solid and liquid waste reduction methods need to be evaluated and further developed. The current adaptations needed for scaling up the IPR system to be more commercial sizes need to be further studied and economically evaluated. Next, okay. Am I at the end of my presentation? So thank you for listening, sir.